Hello everyone, and welcome back to another video. And as promised, today we'll be taking a look at the PCB of the Zotac RTX 3060 Ti Twin Edge. This PCB also happens to be the reference PCB for the 3060 Ti, so this is going to be pretty much the same that you will get on most 3060 Ti's, especially the cheaper ones. Or also like generally all the cards from brands like Palette, Zotac, GameWard, Inno3D, maybe the cheaper Gigabyte cards too. A lot of cards are using the reference PCB this generation. So this doesn't just apply to the Zotac Twin Edge card, this applies to a wide range of cards. So if you see a PCB that looks like this, you can also apply this video to that card, even though it might not be a Zotac one. So let's get into the PCB, and let's start with our vCore VRM, shall we? So we have a 1, 2, 3, 4, 5, 6 phase. And our power components are the AOZ 5311 DR MOSes, and these can handle 55 amps. So that's not all too bad. It could be better. You can see right here there's 2 more possible phases on this PCB. There are, like MSI has a card that has 7 phases. I don't know if there's actually a 3060 Ti with 8 phases. There are some 3060s with a 10 phase, but I don't know if they're 3060 Ti's. It's a bit weird. But yeah, the reference PCB has a 6 phase. The 2 extra phases here exist, I'm pretty sure, because the reference PCB 3070 also uses this PCB as a basis, and that one will probably have the 2 extra phases populated. But anyway, so the 3060 Ti, and as far as I know also the 3060 non-Ti reference PCB, get a 6 phase with 55 amp DR MOSes, and that's not too bad if you ask me, because the card is at max consuming something like, so at least for this card right here, the default power limit is 200 watts, and it can be extended to 220 watts, and that is well within the capability of this VRM. You can compare this VRM to, for example, the GTX 780 reference VRM. That one was also a 6 phase using 50 amp DR MOSes, so slightly weaker power components. And that card could easily hit like close or even like at 300 watts of power consumption if you overclock the card a bit. Now, admittedly, the 780 ran at more voltage than a 3060 Ti does. A 3060 Ti, when power limited, will hover around 1 volt or slightly below it. When not power limited, it will max out at 1.1 volts. A 780 runs at also between like 1.15, 1.18 volts, so slightly higher voltage on the 780, which leads to a slight reduction in current draw. But the general power consumption of this card is still a rather big difference, at least if you don't flash a higher power limit BIOS. Speaking of higher power limit BIOSes, I have been told by a person who had this same VRM on a 3060 non-Ti that it can apparently handle 334 watts, because that's what they ran on the card. I wouldn't run that much long-term through it, but for benching, the VRM can handle that, is what I've been told. So, yeah. If you ask me, if you want to flash a BIOS with a higher power limit, because 220 watts is not enough to keep the card from power throttling, it will pretty much always power throttle. If you ask me to stay safe, I would go look up like a 250 watt BIOS. That might still power throttle, but it will get you like a higher load voltage and better clocks and just more performance because of it. One thing you could also do is just look up all the other cards that also use the reference PCB and then get the highest power limit available for those cards, since it's the exact same VRM. It's supposed to work like that. So that's a pretty safe way to get a higher wattage BIOS if you want to. Assuming, of course, there exists one. It might be that NVIDIA enforces a very strict maximum power limit on the reference PCB. That could be the case. But from what I can see, this VRM can handle a lot more than 220 watts. As for the PWM controller, it is right here on the back, and it is a UP9512R. So the UP9512R is a slightly less sophisticated version of the UP9512P. The UP9512P is supposed to be working with smart power stages. So it has I think a ref out pin, which is used for current sensing, like it hooks up to the current sense circuit of the smart power stage. But since we have the RMOSes on this card, they don't have integrated current sensing. Therefore, we use a UP9512R, which has instead DCR current sense. It uses the DC resistance of the inductors. Basically, it uses the inductors as shunt resistors to try and measure current. It's not very accurate, but it's accurate enough to phase balance a little bit. So that's what the R means. There's also there's an UP9512S and then one more, which are 4-phase variants of the controller, but the R and the P are both 8-phase variants. So this can go up to 8 phases and also 2 MHz switching frequency. As to what actual switching frequency this one uses, I don't know. I would assume something around 300 to 600 kilohertz. And as for the actual phase count, this controller is running as a 6-phase. Quite obviously because, well, we only have 6 phases. As for volt modding this controller, it is quite easy to volt mod, and there's 2 ways to volt mod this one. Now the UP9512 is a updated UP9511, and the main update that the 9512 adds is that it has a I2C interface. So if you look up the pinout and find the SDA and SCL pins, you can hook up an Elma EVC to this. And you should have pretty much like just direct low-level access to the controller itself, and you should just be able to tell it what kind of switching frequency, what output voltage. You might even be able to set overcurrent protection and things like that. I don't really know how many features this controller has because I never used an EVC with it. It shouldn't have too many options. It is a rather simple I2C interface, but you should at least be able to set voltage and maybe switching frequency. And then the other way to volt mod this is that, well, it's a modern NVIDIA card, and modern NVIDIA VRM controllers need to follow NVIDIA's PWM vid spec, which means that this controller has 3 pins called VREF, ref in, and ref ADJ. That's a J. So VREF is always 2 volts. Ref in, whatever voltage ends up at this pin is the voltage that the VRM will put out, and ref ADJ is connected to both of these pins through a voltage divider, which can skew how the voltage divider works, which changes what voltage ends up at ref in, which is how the card controls things like idle and load voltage transitions and power throttling. And what you can do is you can just disconnect the ref ADJ pin and then add a potentiometer from VREF to ref in to skew the voltage divider in whatever way you want. And that's how you get full manual voltage control on a modern NVIDIA card. And the beautiful thing about this is that this completely disables any kind of driver interference. Like the GPU driver can try whatever it wants, it will not be able to change your vCore voltage. Now the one problem with this, of course, is that this is only really useful for benching because the card will, of course, no longer go to idle voltage, which will destroy your power efficiency. And just for dailying, you probably, like, just because the power efficiency and also for daily, you probably want ref ADJ to be connected. So what you can do, that's actually what Buildzoid did on his 3060 Ti Gaming X, is actually, I'm pretty sure this part of the PCB is the exact same. So if I remember correctly from watching his video, this resistor right here, gonna have to make this a little bit smaller. This resistor right here should be ref80J, and what he did is he desoldered the resistor and soldered it back on like this, and then soldered these two pads together. So like that, ref80J is no longer connected to ref in. But what you can do is you can, of course, connect a switch. So if you close the switch, it will now act like the resistor is angled the right way again and connected. And if you open the switch, well, ref80J gets disconnected. So that's a pretty easy way to just disable ref80J if you want to, and then reconnect it when you want to run the card daily again. So that's pretty cool. So yeah, that's how Buildzoid did it, and I think that's actually kind of the best way to do it if you want to both daily and bench the card. Just change the orientation of the ref80J resistor, because you don't want to lose that. You don't want to lose this resistor. It has a very specific value that you can't really buy. So if you lose it, you're gonna have to make a really weird assortment of some parallel resistors to get the resistance right. So don't lose this resistor. Just solder it on in a way where it's not directly connected, and then use a switch to manually toggle whether it's connected or not. That's how Buildzoid did it, and I think that's how everyone should do it. Then we have more VRMs on this card. Specifically, we have a two-phase memory VRM as well. So this card from Tech Power Up, I always forget to mention it. The images are from Tech Power Up. Thanks to Tech Power Up for making these high-res PCB images available on their website, as well as giving some insight as to what components are on the card, because the images are not that high-res. So yeah. But anyway, both the Tech Power Up card and the card that I ended up with were using Samsung's 8 gigabit C-Die GDDR6. So this is G6S8C. And Samsung chips historically have usually scaled with voltage. So you want to be able to control your memory voltage as well if you have Samsung chips. Hynix chips, I've heard, actually like to be undervolted, so you also want voltage control on those, but skew it actually downwards, not upwards. And if you have Micron chips, it tends to be a mixed bag. Some chips scale, some don't. I guess you'll have to find out yourself. But yeah, so we have a two-phase memory VRM using some dual NFETs. Let me look up what exactly these are. These are Sinopower SM7342. So yeah, just dual NFETs. It's just a 256-bit memory bus. So this will probably run fine on a one-phase. Two-phase obviously better, gets even better voltage regulation, but yeah, the MOSFET's gonna be fine. And the controller is here on the back, and that is another UPI controller. It's a UP1666Q, and this one is volt moddable in the exact same way as the UP9512. So this also has a PWM vid, and it's gonna have a VREF, a ref in, and a ref80J pin, and you can do the exact same thing. On this one, you might actually not have to disconnect ref80J, because the only kind of voltage changes that you have on the memory rail is that it might go down slightly in idle. So the driver is not gonna be messing with your voltage a lot, so you can probably just leave ref80J connected, and then just if you leave ref80J connected, basically what you're doing is you just add an offset, whereas if you disconnect ref80J, you can set an exact voltage. But since the memory voltage doesn't really tend to jump around a lot, you can probably leave ref80J connected for this one. Then we have more minor rails. We have an inductor and what looks like a little power component right here. I am not sure what this is. This might be for fan control, though the fan connectors are in a completely different place. This might be 5 or 7 volts for gate drive of the MOSFETs and the AMOSs. I am not really sure. I just saw an inductor and what looks like a power component next to it. This could be many, many things. And then we have two more minor rails over here. I don't exactly know what these are, but I'm gonna guess that this is 1.8 volts because it is very close to the memory chips and the BIOS chip, which is what need 1.8 volts. And I'm gonna guess that this is the PEX rail because it is very close to the PCI Express slot and the display outs, which is what PEX rail is responsible for. So yeah, the 1.8 volts rail, not really that important. You can probably leave this alone. The PEX rail, if you're planning to do sub-zero overclocking, specifically liquid nitrogen, you should probably volt mod the PEX rail because raising the voltage on the PEX rail can help with cold bugs, cold boot bugs, display dropout issues. Just if you run into problems with the card getting too cold and no longer wanting to cooperate, raising the PEX rail can usually help. But if you do ambient overclocking or just slight sub-zero, you probably don't need to touch the PEX rail. So then, one last modding thing, shunt resistors. So we actually have 3 shunt resistors on this card, even though we only have 2 inputs. So we have this right here, that's the 8-pin shunt resistor. It goes through this 12-volt input inductor, and then it seems to go into this mystery shunt, which I don't know what it does. And then for the PCI Express slot, we have the PCIe shunt right here. That seems to go through this little inductor here and then go into an internal layer and probably feed a bunch of the vCore VRM and maybe also one phase of the memory VRM. Like, as far as I know, usually you have one phase. So the PCI Express probably powers the minor rails and then at least one phase of core and memory, because if you don't plug in your 8-pin, the card will still be able to power up and tell you to plug in the 8-pin. If you don't have at least one phase of every VRM on the PCI Express slot, you will just get no image. So that's why usually you have at least one phase of every VRM on the PCI Express slot, and then the rest is usually handled by the other connectors, the 8-pin in this case. So, yeah, as for shunt modding, works the same way as any other NVIDIA card. You have 5 milliohm shunts on the PCB, and you can either remove these and replace them with lower rated shunts, or just put a different like a different shunt on top of it and put them in parallel. What tends to work well is to just put an 8 milliohm shunt on top of the existing 5 milliohm shunts. That gives you an effective resistance of 3 milliohms, which is usually just above the level where the card goes into safe mode. Because if you put a 5 milliohm on top of a 5 milliohm, at least for the 20 series, the card would go into safe mode, because then the power readings would be too low and the card would realize that something is off. So yeah, so what I would do is put an 8 milliohm shunt on top of this one, and then see what it does. And if it changes nothing, I would also put an 8 milliohm shunt on top of this one. But because I don't really know what the mystery shunt is for, I would leave it alone for the beginning. But if it just makes your mod not work at all, then I would also just put an 8 milliohm shunt on top of it. As an alternative, you can of course use the, I forgot what it's called, Debauer had it, demoed it a while ago. So Elmer offers a little PCB with a P-channel MOSFET that you can solder on top of a shunt. And that P-channel MOSFET uses its internal resistance basically as a selectable shunt resistor. So by skewing the gate voltage of that P-channel MOSFET, you can change its internal resistance and like effectively have a shunt mod with selectable resistance, so that you can put it as low as possible, like right above where safe mode kicks in. If you want something a little bit more fancy, you can of course try that, though just putting like 8 milliohm shunts on top is already gonna be like, it's already gonna make your power limit not twice as high, because you're going from 5 to 3 milliohms, so like 2/5 higher basically is what you get. And yeah, so that should cover all the VRM power components and all the mods. So let's talk about capacitors. So I'm gonna clean up a little bit because the PCB is kind of crowded now. And yeah, so as for capacitors on the card, I mean, it's a reference PCB. Reference NVIDIA PCBs don't tend to have much in terms of capacitors, and this really isn't an exception, except for one part. This thing has a really nice input filter. And the reason why I pay special attention to the input filter is if you've ever seen a 6900 XT or a 6950 XT, you know that these things have an awful input filter, which actually hurts their overclocking capability quite significantly. So ever since that card, I am also paying attention to the input filter, which I previously thought is not all that important. And to be fair, it's not as important as output filtering, but you should have a decent input filter, and this card does have a very decent input filter. Like, we have one capacitor for each memory phase, and we have more than one capacitor for each vCore phase, even if we had the full 8 phase. Like, oh no, actually, there's 8 capacitors, but there's spaces for 2 more. So if we had the full 8 phases, you'll probably have 10 caps. So yeah, more than one capacitor per vCore phase, which is enough. Like, that's enough. These are also these are 560 microfarads. So like the red ones are 560 and the black ones are 330. That is a lot for an input filter. Like the 6900 XT, I think, has like 170 or 180 microfarads. And then most other cards tend to have like 270 microfarads. This thing having 330s and 560s, like 560 is something that you can somewhat regularly see on an output. So that's quite nice. I have to say that maybe these were actually upgraded by Zotac. So like the reference PCB determines the layout, but the AIBs can change some part selection. And capacitors are like the thing that's most commonly swapped out because Zotac likes to increase the capacitance of their capacitors. So other reference PCB cards might not have that higher for capacitance, but even if they don't, just the sheer amount of capacitors is pretty good. Output filter, this one was probably, oh, why did that just happen? This one was very likely upgraded by Zotac because these are 1200 microfarad caps, and as far as I know, the only brands that regularly use 1200 microfarad output capacitors are Zotac and Galax for the Hall of Fame cards. Most other cards will probably have 820 microfarad caps. That's usually the standard. The memory also has 1200s. So these have a bit more capacitance, which might help a little bit. I don't think it will help that much. The output filter on this is admittedly a bit anemic, because this is all you get. Like, you have 6 1200 microfarad 2.5 volt caps, and then there's nothing on the backside. I'm a bit disappointed actually here because like this empty space right here is basically perfect for having solder points for SMD polymer capacitors, like these. These would perfectly fit into that space. As to why those might not be there is, like, you can see how there's like all these signal traces going on here. The reason why these don't exist is probably because the card doesn't have enough PCB layers available to actually have those solder pads there, because the layers needed for signaling. That's my theory. If the card had signaling in a different place or more layers, I'm pretty sure we would have had at least solder points there. So yeah. Then behind the core, we do have actually a decent amount of filtering. Like, we get 4 SMD polymers for the core, like a bunch of multi-layer ceramics too. Like, that's my theory as to why the output filter for vCore is not all that substantial, because this card has quite a lot of filtering directly behind the core compared to what we used to get in previous generations. And filtering directly behind the core is a lot more effective than having it at the VRM output, so therefore the card probably doesn't need such a big output filter, is my theory. Same goes for the memory chips. That's a lot more capacitors than you tend to see on like an AMD GDDR6 card. So yeah. But like in general, the output filter's not all that great. But again, I don't really think it necessarily has to be that great, because like it's a less than 300 watt card. Like it's 200 by default, 220 if you overclock it, even though the VRM could probably like do 250 just fine. But that's the power limit that this card ships with. And for that, this output filter is just fine. Like, yeah, that's just fine. So yeah, that would be it for the RTX 3060 Ti reference PCB. Yeah, overall, like, it's better than I thought. Like, compared to the 2060, as far as I know, the 2060 had like a 4-phase or maybe a 5-phase. So this is at least like 1 or 2 more phases. The 2060 was probably also on like 50 amp DR MOSFETs. This has 55 amps. Like, it's just a bit better. Well, the power consumption should have stayed roughly the same. So that's nice. So even though the reference PCB is basically the cheapest variant of a 3060 Ti you can get, this VRM is fine, if you ask me. Like, it can pretty easily handle more than the stock power limit. So yeah, I kind of like this PCB. It's nice. And yeah, thank you for watching. Hope you enjoyed, hope you learned something, and until next time, goodbye.